As we've already seen, the derivative can be thought of as the instantaneous rate of change of a function. So we're going to explore a little bit more about what it means for the derivative to be the rate of change. And we're going to start by using this particular example of an object that's moving along a horizontal line, and its position at time t is given by this function s of t. Okay, so the object moves along. This is a positive direction. This is a negative direction. Okay, and at time t, whenever t is, okay, wherever that object is at time t, that's the value of s of t. Okay, and so s of t is this cubic polynomial. And so what I want to do is I want to show you a graph of it. It looks like this. It's a cubic. It goes up and it kind of goes through the axis at 3, and then it curves back around. It goes down all the way down to here and then goes back up. Okay, and so I'm going to kind of draw a picture of this, and we're going to call this the position. The position of the function. And so the position is something, you know, like this. It kind of goes up and then it curves, it goes way down, and then it goes back up like this. Okay, so this is t, this is s of t. This graph is like y equals s of t. Okay, so now this is not the path that the particle takes. Okay, so the path the particle takes is just along this horizontal line. Okay, so what this gives is it gives, for every time t, it gives the position of the graph, or of the particle at that time. So like this is 3, right? So at t equals 0, the graph, or the particle's actually starting out here, and then it looks like it increases a little bit, stops, and then here it goes back down, and then like where it crosses the axis, that's where it's at 0, and now it's going into the negative numbers, and then it looks like it's going to stop and then turn back around and go this way, and then it's just going to keep going. So it's like it goes like this, down that way, and then this way. Okay, and so it kind of does a little zigzag is what it does. Okay, so now let's consider the velocity of this particle. So the velocity is the speed of the particle. So suppose t is in seconds. Suppose this is in seconds and this is in feet, right? So the velocity actually gives the rate of change, the feet per second that the particle is traveling at different times. Now there's a couple ways we can do it. We can look at this graph and look at the slope of the lines. Like here at 0, it has like a slope of, I'm not sure what that is, okay, but a positive slope, and then it goes and it keeps getting less, and then at this point it's 0, right? So we could say s prime, and let's give this point a name. We'll call this C1. So at s prime C1, the slope is equal to 0. So the derivative, let's actually zoom in, the derivative is equal to 0 at that point. And then when you get to this side, they're negative, right? So, and then it kind of, as you go here, it gets steeper and steeper, but at some point it has to start getting less steep, right, until you get to here, and then it's 0 again. So we'll call this C2, and then we can say that the derivative at C2, the velocity, is 0, and then it turns, and then it goes back this way. Now the slopes are positive again. Okay, so when you look at this, this C1 and this C2, those are kind of important points. It's where the graph turns around, right? And in particular, the tangent line is horizontal at those points. It has a horizontal tangent line. The slope of the graph at those points is 0. Okay? And those are actually, like, that's a maximum and this is a minimum. It's when the graph takes a turn. And so we're going to call these points critical points. And one thing we're going to be doing in the next chapter is we're going to be looking for those critical points, because those are where maximum and minimum values of the function occurs. Okay? And also those critical points are where the velocity is 0. So it's where the velocity graph goes through the axis. Okay? So I'm going to draw this graph here. And then we have like C1 and C2 here. And we know that the velocity at those points are 0. Okay? So now the other thing we know is the velocity is positive whenever this graph is rising. Okay? Or when the slope of the tangent lines, those lines have positive slopes, the velocity is positive. And then when the graph is falling, like it does from here to here, then it's negative. Okay? So and then from here to here, it's positive again. The velocity is positive. Okay? So it looks like on this side of C1, the velocity is positive. On this side of C1, the velocity is positive. But between C1 and C2, between these 2 points, the velocity is negative. So it's like negative here. Over here, it's positive. Okay? So it's almost like positive, and it's slowing down, going to 0, then it's negative. It almost looks like a parabola, doesn't it? And this actually makes sense because the velocity is the derivative of the position function. So I'm going to take this derivative, and I get 3t squared minus 5t plus 3. Oh, and I made a mistake. This actually is 2 here. This place here is 2. There. But this one is 3, isn't it? So this is like a parabola, and it does look like it, you know, if you have 1, 2, 3, it goes through the axis at 3. And these are the roots of that parabola. So it looks like it kind of goes down. I didn't do it very good. But this is what it looks like. Okay? It's a quadratic equation. And the reason this looks so funny is I was trying to get this to cross the graph at 3. So 3 must be way up there. Okay? But this is a parabola. It's a quadratic equation. And that also fits the slopes of these tangent lines, doesn't it? So there's 0 here. It's positive here. It's negative here. And notice it's negative close to 0, getting steeper and steeper in a negative direction, but at somewhere it has to reach a point where it's the steepest, and then it's going to turn back around and get more and more gradual until it's 0 again. So this steepest point here, where the velocity here takes a turn, or where the velocity reaches a minimum value here, or you can think when the velocity has a horizontal tangent line, that's when this graph changes from being concave down to being concave up, wherever that point is. And it's not necessarily at the x-axis, but wherever that is, and that's called the inflection point. Inflection point. So where a graph changes its concavity is called the inflection point, and it's where the velocity graph makes a turn. Okay? So now let's think about this here. Let's take the derivative of the velocity, and if I do that, I'm going to get the acceleration, right? So this is the acceleration of the particle. This is so the velocity is feet per. This position is feet. This one is feet per second, right? Acceleration is feet per second. And so you can actually simplify that into feet per second squared, right? This is how many feet per second the graph changes per second. So how much the velocity changes every second. Okay, so this is the rate of change of the velocity. So when the particle speeds up, it's accelerating. When it slows down, it's deaccelerating. Okay, and so what we know here is, if we think of this just as a derivative of this graph, we know the acceleration is 0 at this point, and that's actually that inflection point. Okay, the acceleration is 0. So let's actually draw a graph here. And I know whatever this graph is here, at I, this graph is going to be 0. Okay, and so we notice over here the slopes of these lines are negative, and then they get more and more flat until they become 0. So it's negative like this, it goes to 0, and then it's positive in just the same way, and it gets more and more positive. And so it's negative, so it's negative, so I showed the wrong thing here. So the slopes are negative, so they're starting out more negative, getting less and less negative until you reach the inflection point, and then the slope is 0, and then it becomes more and more positive. So it actually looks like this. It actually looks like a line. And this makes sense because what I can do is I can take this graph and I can take the second derivative, or I can take the derivative of the velocity, which is the second derivative of the position. And if I do that, then bring this down, this would be 6t minus 5. So this is like a line where this is like 5, right? And the slope of this line is 6t, or is 6. So this is the acceleration. So what we see here is, if we have the position defined by a cubic, the velocity is a quadratic, and then the acceleration is a linear function. In this case, the acceleration is constant. Okay, the velocity is a parabola. This is the position. Okay, so one of the things about this then is, with the rate of change, okay, the second derivative has a meaning. The second derivative is the acceleration of the graph, or the acceleration of the particle. The velocity is the speed, okay, and then the acceleration is the change. It's the change in the rate of change. Also notice that when the particle is moving this way, the velocity is positive. Okay, so it's moving from here to here. At C1, though, at C1 it starts going back towards 0 again, and now the velocity is negative. So this direction is positive velocity. The velocity is positive. In this direction, we have negative velocity. So if it's moving in this direction, it's negative velocity. So the velocity is actually, the sign matters. The sign determines the direction that you're going. And we can actually define the speed just to be the absolute value of the velocity. So then that's talking about just how fast the object is going. It's not interested in what direction it's going. So the speed is just the magnitude of the velocity, but the sign is the direction that it's going. Okay, and so this is the function, the first derivative, the second derivative, and there's actually a third derivative, and that's called the jerk, and we're gonna look at that in our next example. It'll make a little more sense with our next example, but it becomes more and more difficult kind of to think about and to relate these together. So it takes some concentration here, okay, and some you got to think about that. That's why these actual physical examples help you think about what's going on here. Okay. One other thing is, let me just make a point here that this constant here could have been anything. I could have had this, let's say this constant was 200. That would have moved this graph all the way up to 200. But it would have been the same graph, and so the slopes of the tangent lines would have been the same. And so this would have been the velocity no matter where the graph is positioned vertically. So you could raise it up or down, but you would get the same velocity, the same acceleration. So a constant doesn't change the velocity and the acceleration. A change in the constant, a vertical shift, because those slopes, the tangent lines, are sloped the same way. Okay? So now, here's another example. So let's say we have a rock is thrown up off of a 250-foot cliff at an initial velocity of 75 feet per second. Okay? And it's going to have, at time t, it's going to have the following height. So notice this -16, this is half of the acceleration due to gravity. So we can say acceleration due to gravity is equal to -32 feet per second squared. So the acceleration due to gravity is -32 feet per second squared. And so this is going to give us the height of the rock if we're going to throw it up at an initial velocity of 75 feet. So this initial velocity here is the coefficient on the t term, and then it's off of a 250-foot cliff. And so the constant term is the height. Okay? So in general, you could say the height of an object is 1/2 the acceleration due to gravity, t squared. And the acceleration due to gravity is always negative, because downward is the negative direction, upward is the positive direction. Okay? And then it's going to be plus v naught times t, where v naught is the initial velocity plus h naught. And so this will actually give you, for any acceleration due to gravity, so if you're on another planet or even on a high mountain or something, the acceleration due to gravity will change a little bit. This is the initial velocity, that's the initial height, and that'll give you the height of the object at time t. Okay? So now, let's look at these graphs here. The position. So the way that this graph works is like this. You got like 250 feet, and this object is thrown up, and it's going to reach a maximum height, and then it's going to come down and hit the ground at some point. Okay? Now this isn't the flight of the rock, this isn't the path that the rock takes through the air, because this is time here, and this is the height. So this is for every given time how high the rock is. Okay? So this is assuming that you're right here on the edge of the cliff, you throw it straight up and it comes straight down. So it's not necessarily the parabolic path that the rock takes. Okay? Now, let's think of the velocity of this rock. Couple ways of thinking about this, okay? One way is looking at the slope of the tangent lines. Like here at 0, it has that slope. And then as you go to this point, these are positive slopes, but they're getting less and less until you reach this point. And this is kind of a critical point. And you got a slope here. Let's say h prime of c is equal to 0. Okay, and then after that, the slopes are negative. Okay, so what you got here is you have a rock, and the velocity is positive until you get to C, right? And then it's at C it's 0, and then after that the velocity is negative. Okay, and so here it's just whatever the slope is at that point. So, and then it goes down to 0. And we know that this is going to be a straight line, actually, because if I take the derivative of h, I'm going to bring that down. I'm going to get negative 32t plus 75. So at time 0, this is actually like 75, isn't it? 75 feet per second. okay, and then it's gonna go to 0. So this isn't it hitting the ground, this is it's reaching its maximum height, and then now it's headed back towards the ground. So remember, this is the velocity at time t, it's not the height of the rock, okay, and this is the maximum height, and this is the slope is negative, okay, and it has a constant velocity here and a negative slope. The velocity has a negative slope. I shouldn't say it has a constant velocity. I should say that the velocity is decreasing at a constant rate. So what is constant is the acceleration, right? The acceleration, and that's like the second derivative here of the height, which is the derivative of the velocity, and that's a negative 32. Okay, and that is constant. So, and it's a negative 32. So it's like you have negative 32 here, and it's just constant. This is h double prime of t. H of t. H double prime of t. This is the acceleration. Oh, sorry. This is the acceleration, and the acceleration is constant in this case. And that makes sense because an object is going to change, it's going to accelerate or change its velocity only when there's a force acting on it, and in this case it is changing its velocity, but the only force acting on it is the force due to gravity, which is a negative 32 feet per second at all time, or feet per second squared. That's the acceleration due to gravity. Okay, so that acceleration is constant, acting on that rock at all times. It is constant. Okay, and so again, the position, the velocity, and the acceleration, the function, the first derivative, and the second derivative. In this case, you have a quadratic, a linear, and then a constant function. And so the third derivative here would actually be 0. The third derivative of a constant, the derivative of a constant is just 0. Okay, and this will actually make sense. So let me show you one more thing, and this is the notation that we're kind of using. So the position can be thought of as the first derivative. The position can be thought of as the original function. The velocity is the first derivative. The acceleration is the second derivative. And then the jerk is the third derivative. And oftentimes, instead of writing this, because that gets a little kind of a little cluttered here, they would do like S, and then in parentheses they would put whatever derivative it is, because you could take the fourth, fifth, sixth derivative. In Calc 2 you do things called Taylor series, and you're going to be interested in higher order derivatives. So first, second, third, 10th, 100th, 1000th derivative. Okay, so these are the main ones that we think about. By the time you get to jerk, it's kind of hard to think about what the third derivative means physically. But this example kind of helps here, because you can see that the jerk in this case, so in other words, j of t, which would be h3 of t, is just equal to 0. And so think of the third derivative as the rate of change of acceleration. So when you hit the gas, then you start speeding up. So the rate at which you're speeding, okay, up, the rate at which your acceleration is increasing, but what happens, you kind of lurch forward, or if you hit the brake, just slam on the brake, the rate that the car is deaccelerating, when you slam on the brake, then it really decreases faster, and that causes that jerk again. So you really, that idea of jerk makes sense, because when you change the rate at which the velocity is changing, changing the rate of change. So you can see it gets really confusing. You would get that jerk, right? But with the falling rock, does that rock ever lurch forward, or does that rock ever have a jerk as it falls down? Well, no, it just keeps speeding up until it hits the ground, and so the jerk is 0. There is no, in a sense, no jerk, right, in that case. And so it makes sense here to call that jerk. The other thing is I wanted to show you this notation, which we haven't looked at yet. So, and this, we're going to finish this video up with this. So, S of t is equal to y, okay? If we say that it's equal to y, then the velocity is dy dt, and we've used that. This is the Leibniz notation. The acceleration is the derivative of the velocity. So it's d dt of, and then you would put dy dt inside the parentheses. That's what you're taking the derivative of. But then if I just multiply it across like this, what I would get is I have 2d, so that's like d squared y over, and this is dt times dt. So then I could say dt squared. And that's really kind of weird, but this is how you write the second derivative in Leibniz's notation, second derivative. So that's the second derivative. So similar here, the jerk is the derivative of the second derivative. So d dt of the second derivative. And so if I multiply these across, I get d cubed y over, oh, sorry, and this should be squared here, because I'm putting this into there. So that's a squared. So dt times dt squared is dt cubed. So in other words, like if you have the 10th derivative, right? The 10th derivative would be d dt of d9y over dt9. And you would get d to the 10th y over dt10. Okay, and so when you write a higher order derivative on the top, the number is on the d, and then you just have a y, but on the bottom it's dt, and then the 10 is on the t, like that. That's just how you write those higher order derivatives.